Okay, we're live for real this time. Um, Basically what happened there is I forgot that I was trying to enable debug symbols for Mesa so that maybe I could help um, debug like some of the crashes in the graphics driver. But um, when I did that yesterday, I didn't actually restart anything between streaming and looking at the symbols. So the symbols were present for what I was doing, but not for what was running for like OBS and stuff. So um, with the debug symbols enabled, OBS was running like way too slow to render the frame at the correct uh, fast enough for 60 FPS. So I couldn't figure out what was going on there. Figured it out, fixed it, and now we're back to nice smooth 60 FPS for streaming. So that's good. Um, so we've got some nice zooming and panning going on for the Mandelbrot set. We can zoom in everywhere. We can look at all sorts of weird patterns, but um, what we're seeing here is floating point precision error. So basically, floating point is not precise enough to render this far zoomed in. I should really change this display to be like a delta. But basically, the delta between like the two positions on this screen are very, very small. Like here, it just looks like 0. It's very, very, very tiny, and therefore floating point is not precise enough to just handle that. Um, Now, you might just say, why don't you just switch to double? Well, first of all, double would still show this issue. For instance, there's tons of these Mandelbrot viewers on the just web internet, I guess rendered using JavaScript or something. So first of all, they're like very slow. You can't just zoom in like this. Like when you try to zoom in on the ones rendered using JavaScript, like the whole screen just goes like blurry, then it like slowly renders the whole thing. It's really quite pathetic, to be honest. Um, we don't have that problem here, obviously, because we know what we're doing. We're not using JavaScript, but um, they are using double, probably not by choice, just because that is what you get when you use JavaScript. Um, and you can still only zoom in so far before you start seeing this. So um, just switching to double is not going to solve the issue, and it's just going to make everything like a little bit slower probably on the graphics card because most graphics cards don't have uh, what's it called, like double precision floating point units. They're like specifically made for just single precision 32-bit floats. um, so what we're going to do is implement something called actually, before I talk about that, so one thing I added is I found a little bit of a code snippet on Stack Overflow. I don't think this line's needed for converting HSV to RGB. So if we treat our index here as like a hue instead of as um, wavelength, we can get some colors, but I don't really like it that much. And maybe not with this. We use something like this, or delete that. Something like this. That's like too kind of gross. Very gross. It'll be better like if you zoom out a little bit more. Yeah, anyways, I'll probably commit that, but right now, there's like some really unsmooth edges and stuff. It's not very nice. So, um, yeah, so we're not going to use that one for now. We'll continue with the old wavelength method, which gives us this nicer colors. Um, like that maybe. Um, so yeah, so what we're going to do here is we're going to remove this floating point math. I don't know if it's just going to be enough to only remove it in the shader, or if we also have to remove it in the C code. It's possible because, well, it's also possible we only need to remove it in the C code for scaling the movement speed. So we'll see about that. It's very, very, oh, and then there's another thing that I found, which is, right, yeah, this is a funny thing that I will show. I don't know if this is like a good place for that. Maybe like around one of these. I made a joke about this being like very like Junji Ito, like Uzumaki um type thing. Then I figured out that there's a funny value for this extra calculation where, well, I'll just show what happens. So that is some very trippy. Um, this is like let's just write out of like a Junji Ito like manga. Pretty crazy. Um, yeah, we won't leave that. It's a little too yeah, ugly. We won't leave that there for now. Also, like this, I think reducing this like will help with it doesn't really help with that much. But yeah, that's cool. Um, so the way fixed point math works is basically what you do is you select some you take you basically treat integers as floating point values, and I'm gonna do this up here for now. So we're gonna do an int shift value, it's a constant, and it's gonna be equal to 28 or 29. Uh, Start with 28. Um, so for fixed point, what we do is we take an integer and then we say every bit lower than 28 is used for calculating like fractional values, and every bit above 28 is used for whole numbers, like whole integer numbers. So on a system with it's really, I think it should be like 29, but on a system, so in GLSL, in OpenGL, integers are all 32 bits. I don't think you have like any choice about that. So if we have a 32-bit integer and we're going to use 29 bits for the um, decimal fractional value and 3 bits for the whole value, um, that basically gives us a range of whole values of so, and it's going to be signed, so it'll be like -4 to +4. And if you recall before, all of these, this whole area of interest for the Mandelbrot, like this zoomed out area, is just -2.5 to 1.5 and 1 to 1.5. That's doesn't quite seem right, but oh yeah, sorry, that's right. Sorry, -2.5 to 1 and 1.5 to -1.5. Um, so this range all fits within 4. Um, so we don't need to use like any more than 4 bits for or sorry, 3 bits, 2 bits for the number and 1 sign bit for storing the integer component. Then that leaves us 29 bits of precision of floating point component of a like fractional component. So yeah, let us start with that. So for the fraction, so to do that, we're gonna have to do some funny math. Let me think about how I want to do this. first of all, we need like an equation that, for some of this, we're going to need an equation that converts between our fixed point value and an integer. I mean, sorry, a floating point value and our fixed point value. So that will be the first thing we need, which is right. So we basically need to take our floating point value and multiply it by we need to take our floating point value and multiply it by 1 times let me just think. So these numbers can come in fixed point already. We don't have to send these in floating point. They could come in as integers, which means we'd have to keep track of this on the CPU in fixed point. I don't know if I want to do that. So this is gonna maybe be weird, but what we want to do to convert this is we want a UVec2. This is going to return a UVec2. Sorry, just an IVec, I guess, not a UVec. I mean IVec2. So this scale is no longer just this absolute value. First of all, we need to I want to subtract this yet because we're going to run into issues if we do that. What I want to do first is multiply this by the basically there's a scale for the fixed point value. So any fractional component needs to be multiplied by 2 to the 29. Yeah, 2 to the 29, I believe. So 2 to the, it should be 29 or 28, I'm not sure. But 2 to the 29 anyways is just fixed factor, well, it's fine. Fixed factor equals 1 shifted by 28. It should be like shift minus 1. I don't know if this is allowed, but we will see. It should be, but so fix factor times this minus fix factor times that, and then absolute. And then our vector that comes in is from 0 to 1. I think this is fine. So we are going to scale the vector by the scale. I don't know why I have this here. And we are going to add that to the bottom and the bottom right corner. And that's not right. So let's just make this take some values here. So IVEC to top left, IVEC to bottom right, ER. Because these need to be like pre-scaled, so for both of these. So then here, no, we don't need that float thing anymore. I don't know why that was there. This is going to equal fix factor times u top left and fix factor times u bottom right. And then top left, bottom right, and that. And then this is going to be fixed point. And in here, it's just top left, bottom right. They're already scaled. Top left, bottom right. And, oops. Yeah. Not implicitly convert return value to okay. We need to explicitly do this outside, so VF, we'll just call it for now. Oops, X factor, fix factor. Okay, so I think it's actually all of these. So how can you just do that? Can't cast these before I do the multiplication, so probably I just want this to be in float to begin with. And then we need to okay, so that is now valid, except we can't see anything, obviously. Because none of the rest of this math is going to work out anymore. But so yeah, so now Okay, this shouldn't be this. It should be an IVEC 2. These should be integers. Yeah, those need to be integers. So then do we need to do other multiplications? Yes. So the thing about fixed point is that addition and subtraction just work fine. Multiplication doesn't work fine. Excuse me. Multiplication doesn't work fine because if you think of the fixed point values having like a scale, implicit scale built in, when you multiply, you just add another factor of that scale, which you do not want. So you have to divide these by that scale. Um, X, Y, X, Y. So this isn't right. Oh, oops, so that's fine. It's this needs to be this. And where else? Down here, this. Okay. So now at least we have some garbage on the screen. Garbage is better than black screen. Maybe, depending on how you think about it. Can we zoom in on the garbage? Oh yeah, that's cool. What is this reset? No reset garbage. There we go. That's awesome. Yeah. Okay. So, oh, I'm gonna do that. Or is this just not wanting to focus? Yeah, I was just not focused. Fun, 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 fun. Um, okay, so here we still need to do this. This part is fine. This part is not fine. So let us calculate I y. Yeah, like IY. It's a complex value, so I'll just call it IY. This is gonna be equal to the 2 to the shift. If we just multiply by 2, it should be fine because 2 is not in fixed point yet. But so 2 multiplying by 2 is just like a shift left, which works fine in which actually works fine in fixed point. So that part is fine. Let us do then we need to do IY times equals xy dot y divided by. I don't actually know this is gonna work yet because of reasons, but well, our garbage doesn't look like the same garbage anymore. So that's one thing. I don't know why I'm doing this. Oops. Delete this and copy this for now. Well, I don't even need this extra thing, but okay. Yes, I didn't think that was gonna work because for multiple reasons. So first of all, um, yeah, so I don't want to do it like this. I want to actually I want to like write like a multiplication equation for the fixed point. So we're gonna have int um, int uh, fp mul. Well, fp mul kind of, let's do fixed p mul int a int b. And in here, what we're gonna do is um, so a a what's it called? A decimal is equal to a and what's the thing that I want here? One shift one shift 29 minus one, or one shift, yeah, this minus one. I actually need this mask. So in um, decimal mask int fraction mask. This is actually the fractional mask. So in and I don't know if there's like bitwise negation in GLSL, so we can't do that. Let me just think about this for a second. I do have my handy hacker's delight here to help me with any weird bit shift stuff that I don't remember. So a fraction is a and f mask, and then we want to shift this down by the shift amount. So I think we're going to shift it by like half of the shift amount, and then when we do the multiplication, we get let me think about this. So the scale let me just look at this yeah, so when we do this multiplication, the fractional part is going to become So, okay, so let's just do the simple idea first. So if you have a 4-bit number times a 4-bit number, you need 8 bits to store the result. Um, so if you were to first shift that down, both of those down by 2, and then do the multiplication, you would only need the 4 bits. You'd still only need the 4 bits. Now that loses you some precision, so you have to be careful if you do that. Um, Now, I don't know if the arithmetic unit on the GPU has the precision to do this. So normally, if you're doing 32-bit fixed point, you can just do the multiplication. Your result will be 64 bits wide, and then you can shift it down and you won't lose any precision by doing that. But if you do anything like shifting first, you're gonna lose some amount of precision. Um, so I think I'll just try doing it without doing the shifting first and do the shifting after, but um, in that case, though, the result is just going to be equal to A times B shifted by shift. Um, is that right? Is it shift or is it like shift plus 1? That's where I'm like, this is where I'm like a little worried because this might just cause everything to go to 0. Um, let's comment out this loop for now. Yeah. Oops. Okay, so I'll just comment out that loop for now. Um, and then we will do this. Yeah, so I was kind of thinking that was what was going to happen if I just did that. Um, and that is because, yeah. So we do need to be like more careful about doing this. I know this part just works fine still. Um, because of the problem with this. Um, okay, so this one we can't do just do this. Oh, also part of the issue is this comparison is just wrong nowadays. So int comparison equals um, n.0 times fixed factor. Oops. Okay. So that comparison is now correct. Um, that comparison is correct. But this result up here, we need to be like more careful. So I think what I'm gonna do is try this. So the F mask is equal to 1 shift minus 1. And then A float is equal to A and F mask. Then we're gonna do this shift by shift over 2. And then B. So then R float is just equal to A times B. And then the integral part is not F mask. I don't know if this is allowed, possibly, but we're not using that yet, so it's just getting optimized out. Then we're going to do the same thing again. And then RD is equal to oops, AD times BD. This needs to be AF times AF. And then the result is going to be equal to RD shifted by shift ORed with RF. Okay, so that all seems to be fine, but the math is maybe not correct. And is there other places where we're just doing this and it's going to be wrong, such as here? E dot x, scale dot x, v dot y, scale dot y. Okay, I don't know if that's right yet. And then at the end, let me think here. So this looks correct now. Then that part is correct. What about so yeah, here we need to convert this back to floating point first. Z magnitude is equal to square root of to get back to float from fixed, we have to divide it by, we just have to divide by the, so xx divided by the fixed factor. And then use this here. Make sure we're like in the view. This is still working, right? Yeah. Okay, and then let me think here. It might be more useful to just write a little bit of a test program in C and make sure this all just works how we're expecting it to. So I think I might do that quickly. So let's write, move this over here. We're gonna include standard IO. Do in main. So let us make this same function here. I think it's just literally just gonna be the same. So static int shift equals 29, static int static float fix factor equals one shift 29 minus one shift minus 1. Okay. And then let's just go over here and copy all this. Oops. Okay. So this looks fine. And here what we will do is float, we only care about values that are like in this little small range. So float, a float is equal to minus 1.5. I need to be able to like do these things here. So minus 1.5 times minus 1. Let's do like let's do like minus 1 point. So this will be minus 1.5, and then the float will be equal to 1.5, and then fixed point result will be equal to fixed p mol times AF times fixed factor and BF times fixed factor, and then that's going to give us our integer result, and then printf floating point result is going to be equal to this, which should be 2.25. That's going to be floating point result divided by fixed factor. Let's cast this to a float. It doesn't like me doing that. That's fine. That's not quite right. So 0.075. Let us step through this program. So I've added my debugger here. Let's cc dash o 0 dash g3 a dot s dot c. And then we're gonna do got this debugger. Gonna be a bit annoying to use, I think, in main.c, test.c. So then if we break main, we run, go to locals, step. Okay, so locals, we have that A is this and B is that. Okay, A and B shouldn't be the same thing, right? Or should they be the same? I should probably use like just different numbers here so that it's more clear what's going on. Let's do that. I did this wrong, but that's fine. Probably, and you can see this. Yeah, let's use some different numbers. Let's just do this. And we'll do this again. Okay, so A and B should be different numbers, which they are. Now, are those numbers correct? I'm not 100% sure yet, but I guess we can do the. So let's go up here to this and do fixed factor is this, which is correct because I think that's correct. Either that or it's minus. It's supposed to be less than. Okay, well, let's just see. Let's just continue stepping for now. So the A floating point component should be something. The b decimal part is 0. That's not correct, right? So b a decimal part, b decimal part. Why is the b decimal part 0? It should be 1. It should be so that's one problem. Is like first of all we need to we only need to care about that overflow for this part. These should just get shifted by the shift amount. But that's not what's so let's actually have a look here. So what is dmask? I need to know what dmask is in like hexadecimal. Thought it was like I don't know if you can. Oh wait, it's yeah. Oh right, okay. Okay. One F F F F F. So that and then E. That is correct. So D mask and F mask. Um. So yeah. So F mask is definitely correct. So we want the top 3 bits to be integer. Let's pause for a second and go to the washroom. Hello, Fern of Sigma. We're doing some fixed point math here to try and um, escape the accuracy issue of the floating point values. But so far, we are unsuccessful at doing the fixed point. So we are exploring in the debugger what goes on here. So let's do a, should be like the, um, so B is definitely, the top 3 bits of B are definitely 0. Which means that this part is not like fixed factor is not quite correct. Is it really supposed to be this? -1. I don't think that is. Um, so hold on. Um, why is that weird? Okay. Um, so B is now 2, which means that the top 3 bits. Does this like have binary? I don't want to like look at 30 binary digits, but uh, well, okay, octal does also work. Um, like this is still wrong because um, actually octal will work really well here because we need 3 bits and an octal digit is represented by 3 bits. So this is actually octal is probably better than using. Oh, you know what? But this isn't. How many octal things are here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Yeah, that octal that is a little annoying how the person who made this program printed this octal, to be honest. Because sometimes people write octal with like a leading 0 for some reason. Um, I think this is correct though. So we want the floating point result to be, so this B float is a 1, which means that the B in fixed point needs to have a 1 in the third bit. So the third bit should be 1. Um, if the third bit was 1, then in hexadecimal, um, it should be a 2. That would be correct. Yeah, this is now looking correct. I don't really care about that. So, yeah, the fractional part of B is 0. That is correct. That's a problem, isn't it? Eh, that's a problem. So the F mask is correct. Oh, this didn't reload the file. I did not save that. Oh, I didn't save that. Weird. This is not supposed to be like this because the value is small. result is 2. Not quite. The result is minus 1.5. So, still off a little bit here. So let's try that again. So A is 1.5, which means that A should be we are losing like half of this precision, so that might be a problem. But well, yeah. So first of all, there's a problem, anyways, in that if the fractional part of b is 0, then this multiplication is going to give us a 0. Which is wrong. So if we, let me think, if we shift this stuff all down by a half first, yeah, so what if we just, if 0 this stuff, and we say that int result is equal to at is equal to a shifted by so that doesn't really show up, so well, that cropping is wrong, but can get too distracted by fixing this right now, but let us just try this quickly. That is, I don't know why that jumps to the other window. Speaking of which, we'll just put some random other thing up there. Okay, so like that would be good, and then I don't really like this welcome to the chat room message, but oops, I need to make this actually visible. I guess the problem is that we don't want um yeah, that looks like really ugly as well. So well, anyways, I'll just leave that for now. So yeah, let us do this thing. So FA shifted by um shift over two. Sorry, just A shift by, and then B is B by shift over two, and then the result is A times B. And we compile that one. Oops. That's getting closer to what it should be. But that's still not quite right. I think maybe it has to do with this. Let's just try this for a second. We'll try just yeah, so shift needs to be increased. We need to take the seal of that. So to do that, we need to um then do this. And we can go back to this. Oops. Not quite. I need to round it down one, not up one. So okay. Wait, what? How did I go back to three? How is it just like going off by one? Yeah, okay, right. Because before this was correct, I think. Well, it might be like specific to using the odd numbers. This is like the default, so I don't know why I'm doing this. I think it's just because I was using the odd number. Yeah. So it's really because it's only this case, so whatever, that's fine. This is correct if it's odd, and then we don't need this. If it's not odd, you have to use the other factor, but that's fine. Okay. Set AF set BF equal to 1.5, and then stab. Okay, that is correct. Now we can do this. We'll try to do this. So let us just try that for now. All of this can just get commented out. And then what we'll do is do int this is if the shift is like this. AT times BT. Okay. Now that multiplication definitely works. But does the Mandelbrot work? It's not. So let's close some of this junk. Why would that be? So when we get to our I mean, on the other hand, we could do this comparison with I don't think that matters. Not use the comparison, to be honest. Yeah, I'm gonna get it out. We'll keep the comparison. Let me think here. So, oh right, that's a problem. 10 doesn't fit in our value. That is the problem, duh. Yeah, so 10 is not a value that exists in our fixed point representation, so I cannot use 10. Only 4 exists in our fixed points. Like, is this gonna work with 4? That still works with 4. 4 is the maximum fixed point value we can do. So actually, I don't even know if this, yeah, let's set this to, should be fine. So we can now zoom in. Fortunately, it has not slowed down, but we do have like a lot of artifacts and junk going on here. And also the accuracy is admittedly much worse now than it was before. I think that has to do with we're losing the precision in that multiplication. Kind of is not good. Oh, that is interesting. That is very interesting. Okay. Um, let us see about not doing that. I'm gonna need to make another coffee, I think. Um, let me just go and put that on. Um, there is two things we could do here. So, first of all, um, well, we could see about trying to enable see if it's possible to get a 64-bit, see if it is possible to get a 64-bit integer result directly, which we should try first. I should look up first. Otherwise, um, we have to go back to the olden days where you would have to, there's some like, you know, you're smart about it, you can do the 64-bit multiplication um, using the 32-bit numbers and then recombine the result after. And because the result is, um, you won't like lose accuracy the way we're losing accuracy right now, basically. Um, it will still be, limited to 32-bit precision at the end, but um, yeah. So let me think here. So GLSL 64-bit integer. There's like an extension that allows you to use 64-bit, but I don't know if I want to do that because it's not going to be supported necessarily. Um, well, we can try it first and see how that goes. Um, how do you enable these? I think it's like a preprocessor. Let us try, I guess. Like this. Um, how do you do this? So yeah, I see. Okay. Not quite what I did here. Um, this. Okay. Error extension supported, unsupported in fragment shader. Oh, interesting. So, PL 64-bit extension in fragment shader. Hmm. Not really finding how to set this on, and also it's not necessarily what I want anyways. Um, Arithmetic types. It could just not be supported at all. So um, it might be better just to do the look into my handy dandy Hackers Delight here and see what it says about doing integer math with you need to how you can do the multiply with smaller width. Um, I do think it has some stuff in here about doing that, so that is good. Let me take a look here. Page 171. It's talking about multi-word multiplication. So high order half of 64-bit product. So here we consider the problem of computing the high order 32 bits of the product of two 32-bit integers, which is exactly what I'm trying to do here. Um, without using the without having 64 bits be available, basically. So we're going back in time to when, we only had 32-bit computers, or I mean, the similar thing would have been done for, 8 to 16 or 16 to 32, etc. Um, right. So now I remember. Um, the FPS of which the FPS of this is constant 60. Um, do you mean the FPS of the stream? It looks like it's fine on my end. So nothing should be changing in the image. I can zoom in now. So the reason it just looks like this is because I'm doing the fixed point multiplication, but I'm doing it incorrectly. Um, so sorry, and nothing's changing in the image. It's just being calculated every time. Like it's just getting recalculated every time I do the loop. So yes, because um So right now it doesn't have it. I want to get this math worked so we can zoom in properly. Get this math worked out. But once the math is worked out, I want to like animate. I want to have like an animation of it zooming in. So I need to make sure that it's at least 60 FPS. I just have it. I have VSync turned on right now. So actually, this is happening like at 1,000 FPS if I turned off VSync. I just need to make sure I don't slow it down below 60 FPS because then when I go to do the zoom in, it's not going to be smooth. Right, so to do this, multiply. So this extension is not going to be getting used. So there's our little weird multiply here. So this is our fixed point multiply. We're going to have a separate function here that's going to be multiply I word. It's going to take the higher order portion of these, and it's going to return the upper 32 bits. It's not going to return the. Okay, so I can actually probably do this into. Let's do it this way. Let's have two functions. Let's have multiply high word and let's do this low word and high word. So we need to get both the high word and the low word of these multiplications. So in this function here, we need to get the high word some values, and then this is in the shader. This is all in like the fragment shader. It looks like C, but yeah. The thing to know about the fragment shader is that it only supports 32-bit math, and I need to do a 64-bit multiply. Like I need to multiply two 32-bit values together, but the result will be like 64 bits. And I need like the middle 60. I need like the middle bits, not the yeah, I don't need like the low bits or the high bits. I actually need the middle bits at the end. Yeah, exactly. That's what I'm doing. I haven't done this like before, so I'm looking at this book, Hacker's Delight, um, which basically just contains all these sort of like weird, if you need to do some weird and anything that has to do with like low order bit manipulation, you can find it in this book. Yeah, like it. So I think the need comes up on like microcontrollers and stuff, but usually on the desktop you can get away with like a 64-bit integer um, for like anything reasonable. But in the shader we only have 32-bit integers, and I need to. I see. I see. Even on a microcontroller though, like um, I'm sure there's like some use where you need to do that kind of math, but I feel like most of the microcontrollers that they get used for doing stuff that needs math support floating point math, so they're not even going to care about doing this either, to be honest. So we are going to split up. We're going to have an uint, which is a low is equal to int is equal to a and 0 x f f f f. Yeah. And A high is going to be equal to A shift by 16. I mean, yeah, A shift by 16 is what I want. And then, well, according to this should be like signed still, um, which makes sense because you don't want to lose the knowledge about the sign bit. Well, I'm not 100% sure that matters. Um, so then B low equals B and 0x FFF and B high, oops, B shift 16. And then the result, so int result low is equal to A low times B low. And then we need like a temporary value here. So the temporary value is just being used to figure out if this, so we need to figure out like which part of this low word multiplication spilled over into the high word portion. Now, I also might run into some problem here with, well, we will see when we get there, to be honest, but might run into like a problem with the scaling factor that's in these fixed point numbers. um, so t is this temporary value is going to be equal to a low times, sorry, a high times b low plus the low word, oops, the low part of this result. And then result high is going to be equal to sorry, this is all supposed to go into the high word multiplication part. I should probably also move this into C so I can test it, but for now we'll just keep it here. Okay, so yeah, result high right now is going to be equal to, well, I'm going to use the numbers they have here for these other parts. So result part 0, result part 1 is equal to t and 0x FFFF, and then int result part 2 is equal to result part 0, sorry, p shifted by 16, and then result 1 plus equals so a low now, no wait, So sorry, up here this should have been A high and B low. Wait. No. So that's correct. Yeah, this is correct. And then down here, this is gonna be A low times B high again. Oh right. Yeah. Okay. And then finally the result is gonna be given by this is like a little annoying. So actually like a lot of microcontrollers have specific instructions for doing this. I don't think there's a good way we can just do that on the GPU though. So we now need to return the so B high times A high plus result part 2 plus result 1 shifted 16. So this is the high word part of that multiplication. So and then for the low word part, for the low word part, the low word part is just literally this multiplication. Because it's just going to discard the rest of the result. So yeah, whatever. I don't really need this function, but that's fine. Okay. So then our actual result here is going to be we need the we basically need the middle bits of this multiplication, which is and then start playing sound. I guess I don't have desktop. Yeah, anyways, I was muted, so that's fine. We need, I don't need this. I need to see. So we need the, you discard the top, we need to discard the top half of the multiply high and the bottom half of this. So this is going to be equal to high word and 0x FFFF shifted up by 16. And then ORed with the low word shifted up by 16. Sorry. Low word, blah, 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 blah. Low word ended with 0x FFFF 000 shifted down by 16. Oops. We're like used to this. Oops. Couldn't implicitly convert uint to int. Where is that happening? It's in here somewhere. Um, so A low times B low, we have to just like whatever. Okay, so that is fine. Down here, we need. That should all be fine, right? There's a new error that's complaining. Oh, here. That's actually back to our like weird messed up thing from before. Um, I think that's actually related to this fact that the scale is being duplicated. Um, so possibly. No, we can do that. We cannot do that. Yeah, we cannot do that. That is wrong. Um, so it might be better to do these multiplications a little bit differently. So what I was doing before with like extracting the decimal and the fraction, and then doing it based on that. So let's see about doing that. Because the fractional part, um, well, okay, so the fractional part, yeah, it needs to, you still need to add part of it though. Well, you can add the decimal part to the fractional part and it will be fine. Yeah, okay, right. So fractional mask and the dmask. What's like doing in the C code for this? Okay, what's just literally doing that? Okay. So the decimal part of the result, RD, is going to be equal to um, A and F mask, A and B mask shifted by shift. We don't actually have to worry about this part overflowing. That's fine. B. And then we have to worry about the integer part, the fractional part overflowing. So actually we don't want to discard this. I think it's actually we just need to shift both of these down first and then mask off the part that we care about. that correct though? No, because that's gonna divide out. So our result here is like way too big. So which, maybe it's just this mask is wrong. It's wrong here. So let's just do some comments here. So we have 0x, FFFF, and if we have two of these, then our result is going to be it's going to have this range to it. Now, which parts of this are overflowing? So okay, so the parts that are overflow are the amount we want to shift by. So yeah, if we're using, so the lower 29 bits are overflow. Or like underflow, I guess. It's more fractional part than we wanted. And then the higher the higher 3 bits, 4 bits. It's either the higher 3 or 4 bits are overflow. So for the high word, we want to mask out 7. 1. Actually, we have our masks already. I think it's just these masks. So yeah, except it's opposite now. So this is and F mask. This is and D mask. And then don't think we need this stuff. So then we don't want to do this anymore. We want to shift the high word up by not by 16. Not mask it like this. We want to shift the high word up by 32 minus shift, I think. We want to get rid of the higher 3 bits on R. We need to get rid of the higher 3 bits. So we just do that by shifting over by this. Like, I don't really need to do these masks. So if we shift by the higher 3 bits, or shift over 3, that gets rid of the high 3 bits and leaves us with the bottom stuff. And then it's not an OR operation, that's the problem I'm like running into. It's an addition. And that is going to be an addition of the low words that plus low words. We have to shift out all the yeah. Besides the fact that I've made a typo somewhere here. With one too many of these. There we go. So that does not fix the problem yet though. Also, why is this like why is the default position now like way off? Who knows? Let's just zoom in and see what's going on in here though. Hmm. This is assuming that that multiplication high word is correct, which it might not be correct. Um, right, back. It's actually not quite what I have here, where it is. It's not an addition. It is so this part is correct. And this part is correct. It's just shift. Um, and then here it should be masking with the and just ORing directly with this. Masking with the lower 3 bits, so 0x 3 7. No. It's a fun color. There's actually like some weird shade going on there, but okay, so let me just think here. Not that one. Let's just go back a little bit here to what I had. Um, Let me just think about this. I need the high sign part of this thing. So we have to do is first things first is to multiply the lower order bits to figure out if those will overflow into the high part of the word. So let's try this thing that I was doing here. This thing doesn't overflow. Plus, how do we get rid of the integer part? So the integer part is, so that's like, That is fun. Actually, like, curious if this smooths it out. No, not really. Um, I'm still like a bit suspicious about this part of the equation here. Like, one thing to know about the square root, integer square root, is that I'm not sure. Not 100% sure yet. Um, is everything here just correct? Um, like this part specifically. So, one thing I can just do quickly here, probably now, is release this one. Um, huh. So let me think here. So we need to. There's some issue going on with this math. Um, and I think it might be up here. So when you multiply the lower half word, um, the lower half word. So this lower half word here, it cannot overflow. Why is it like half? Why are we doing this? Why? What would part? What? I don't know why this part is here, to be honest. Because like, am I missing a part of this equation that they've got in the textbook? Um, Possibly. Um, like I've got like exactly the math that they've got in this book. Um, Let me see here. So V multiply. I think this part is correct. I think it's just down here where I'm doing this stuff that's going awry. So what I have to keep in mind is that these 32-bit integers have an implicit scale in them. And that implicit scale up here is going to get multiplied. And so we end up with like a factor of scale squared. And we need to get rid of that factor of scale of scale squared, which is we can do by dividing by the scale. Not it's definitely this is not dividing by the scale though. This is no, it should be dividing by the scale, right? Um, so that's all this part does. I don't need that part. Before I tried to get rid of the scale by dividing by half the scale first, but that screws up with the precision. So um, how can I do this without messing the precision up? Because right now we're still having like a precision issue. Um, I need to get rid of this scale. Scale squared is what? I feel like we can handle this the scale in this part of the equation though. Like, what happens if I just lower the scale for now? Um, yeah, it doesn't work at all, and also that's really weird. Whoa, that is really weird. That is fun. Um, that gives some interesting looking colors, but it's obviously like way worse than what I had before. Like, the only problem I have here is that this. Oops, I got my thing stuck. I don't know why. Hmm. How does this work? How can I fix the scale? Um, to fix the scale, I need to do something. Wait, isn't that what's happening down here? Yeah, that's what's being corrected for here, right? I want to clear those lower 3 bits. What if we just clear the... What if we just clear that? So this is the mask. And this is the... This is wrong, but yeah. Um, so I know what I know is that the hmm hmm. So what do we know? So first of all, there's like some other issues as well. When I'm resetting, it's not getting this is not working anymore. This is getting set to the wrong location. Hmm. This isn't gonna fix this part, but the one thing I did see before was that um that's not right, actually. Whatever. That's has nothing to do with anything anyways. So I need to figure out how to do this better. Like basically the mask that I'm trying to create here would be one F F F F one F F F F F F F and then only the top 3 bits of this, which is 7 0 0 0. And then we shift these around to get them back into the correct place. So let's try that. High word equals high word and 0x1 FFFF FFFF low word equals low word and 0x7 FF. Not 7. E. E. Not 7. 7's not right. E. And then we need to shift these around by a different value, which is, yeah, this is right. and then this needs to be shifted down, and then forward. Why does that happen? We get some beautiful dance, some beautiful, who knows what. Whoa. Yes, the high word, we now just need to shift that over by 3, which is this. And then, like, what are these masks? These masks are, pretty sure these are just F mask and mask. Yeah. But that's not correct for some reason. So maybe the low word multiplication is wrong. The low word multiplication doesn't even matter because most of the result is going to be in the high word because like you can get rid of the low word pretty much and it's fine. Like a low word equals 0 for all I care and it's going to be fine. Yeah, like the low word, I think the low word's just like screwed up. Well, how is this looking? The low word shouldn't screw it up that much. Like, why is this or screwing everything up? Why does the low word screw everything up by doing that? Huh. But that doesn't mean anything. That just means that so this is still like an issue though. We're still doing something wrong because this shouldn't be, when I'm resetting, this shouldn't be here. This should be somewhere else. So there's something wrong, I think, related to the sign bit. Like, I don't actually think I don't really think that the sign bit part matters here. Like, I'm pretty sure all of this could just be you, and it would still just work out. Obviously, if I use the right words. Why did I do this? Well, maybe. Pretty sure this math just works out even in UN, so Um, some implementations may not support implicit. Consider casting implicitly for portability. Where is it complaining that it needs to be cast? Oh, here. So yeah, these. Wait, what's it complaining about needing to be casted to? Oh, where? Which part of this does not consider casting explicitly? Int to uint conversion for and operator. Oh, these. That was those ones. So what is like actually screwed up? Like why does this not work properly? Where are we running into the problem? Rid of all this. Go back to here. How long has this been up for? Hmm. Don't really want to just leave it off on this for now, but I kind of want to take a break and maybe go and look up the review the math a little bit so I can get it correct. Um, yeah, I think we will just take a pause for now. Um, thanks for watching, and I will be back in a couple hours to um, fix this math, basically. All right, see ya.